Okay, we're going to look at this example. This is example 3 from our class notes from section 1.4. Alright, so what we have here is a first order nonlinear differential equation. There's two reasons it's nonlinear. I have the y times dy dt here and also y squared. So I have more applied to the dependent variable than just differentiation and multiplication by a function of the independent variable. So nonlinear differential equation. This is separable. So it's maybe not quite as obviously separable as some of the other ones that we've worked on, but let's go ahead and do a little bit of algebra and we'll see that it is separable. I'm going to start by subtracting y squared from both sides. And then if I divide through by 1 minus y squared, I'll have all the y's on the left, and then on the right side I'll just be left with 1. So there we've separated the variables. Our function of t is really just 1 in this case. Remember, at the instant when you divide through by that function of the dependent variable, that's where you may have introduced singular solutions. So here when I divided through by 1 minus y squared, if what I'm dividing through by could be 0, and it could be in this case, if y is equal to 1 or y is equal to negative 1. I use that triple equal sign there just to remind myself that what I'm really talking about here is the constant function where y is always 1 for all values of t. That those are possible singular solutions. So I'll come back and check that at the end. Okay, so we're ready to go ahead and solve this. So I'm going to integrate both sides with respect to t. And on the left side, my dy dt times dt will simplify to be just dy. On the left side, I'm going to use a little u substitution. There are more than one way to do that. You could do a partial fractions, you could do a trig substitution, but the easiest way is to do a u substitution. So I would let u equal the denominator, and then my du is negative 2y dy, which it works out perfectly since I have the y dy on the numerator. I just end up with an extra negative 1/2 when I do this u substitution. Alright, so I'm not going to write out the rest of the u substitution, but let's just write down what we're going to get. So I'm going to get the negative 1/2 ln of absolute value of u, which is 1 minus y squared, equals, and then on the right side I'll just have t plus c. Alright, so this is an implicit general solution. Notice that this implicit general solution does not include y equals plus or minus 1. Right there, I cannot put in y equals plus or minus 1 in that. We're going to go ahead and find an explicit solution though, so let's go ahead and do that. I'm going to start by multiplying through by negative 2. And I'm going to absorb that negative 2 into my plus c there at the end. Next thing I'll do is exponentiate to get rid of the ln on the left side. And then I'm going to use that property of exponents that we've used a couple times in this section. And I won't always write this out, but really the steps here are I use the property of exponents when I have the exponents that are added. I can separate that into two powers of the same base that are times each other. So e to the negative 2t times e to the c. And then c is all possible constants. E to the c is also all possible constants. So I'm going to just replace that with a new c. Alright, so let me go ahead and write that step here. Alright, so there is what I have at this point. Then to remove the absolute values, I'm going to have a plus or minus on the right side. I'm going to absorb the plus and the minus into my c. Alright, so notice in the step before that, c can only be 0 or bigger in that step because the absolute value bars on the left side force the left side of the equation to be 0 or positive. So therefore the right hand side of the equation must also be 0 or positive to make them equal. In this next step though, I'm now allowing negative c values. So the c I've got in this latest step is different than the c's before. But it helps simplify our answer so that it's easier to think about interval of existence and all kinds of things like that. Alright, let's go ahead and finish solving for y. So there's a couple different ways you could handle the algebra here. I'm going to subtract c e to the negative 2t from both sides and add y squared to both sides. Again here, minus c or plus c, c represents all possible constants, so I'm going to just replace that with a plus c. This manipulating the c's often feels very unsafe to students So you want to be careful about that, and if you feel better about labeling them as C1, C2, C3, C4, and so on to keep track of things, you can do that. You will probably find that after you've done enough problems, you'll start to become more and more okay with that. And the reason it's okay, again, is because you're thinking about what that C represents. So if you're a little bothered by this sort of what feels like sloppiness with the C's, just rest assured that it is okay. Those of you who know me know I'm not sloppy with notation, and so I wouldn't be doing this if it were not okay. All right, so I'm going to go ahead and finish solving for y. I'll need a plus or minus square root. So that really means I have actually two general solutions. All right, so those are general solutions. The next thing I would want to look at is I'm going to go back up here to where I thought about some singular solutions, and I want to think about whether those singular solutions are included in my general solutions. So what I'm looking for down here is, are y equals 1 and y equals -1, are those included in these general solutions? And they are. If c equals 0, then I get y being the constant function 1 and y being the constant function -1. So in this case, I don't actually have singular solutions because those ones that were possible singular solutions are included in my general solutions here. All right, the other thing that we were given was an initial condition, so we're going to go ahead and see if we can find a particular solution, or maybe solutions satisfying that initial condition. So our initial condition was y of 0 equals -2. All right, so when I put that into that first general solution, pause and think a little bit before you just jump into the algebra. You get -2 equals square root of 1 plus c. The left side of this equation is negative. The right side of this equation is positive. And so therefore they cannot be equal to each other. So this one is not true. Y of 0 equals -2. There's no choice of c that makes that general solution satisfy that initial condition. The other one, however, when I put into the second form of the general solution that I have an equation here that's true. I've got -2 equals negative square root 1 plus c. So that's true when c equals 3. You can do the algebra here, multiply through by -1, square both sides, and solve for c. All right, so I do have a particular solution that satisfies the initial condition, but you do have to be a little bit careful about paying attention to negatives and things like that, all that algebra that you learned a long time ago and hopefully didn't forget. But you have to be really careful about some of those little things, otherwise it's easy to sort of pick up the wrong solution and just write down something that seems like it should make sense, but if you go back and think about it, you realize it doesn't actually make sense. So if you just plow through with the algebra here, you might end up writing down a solution that doesn't actually work. So just little things to be careful about. All right, when I think about interval of existence, I need to think about where this function is continuous and differentiable. And if you think about differentiating a function with a square root and what the derivative of that is, you might realize that if there's any value of t that makes that expression inside the radical 0 or negative, then we need to avoid those values of t. So when I'm thinking about the interval of existence on this one, I want to start by maybe thinking about that expression inside the radical, and if that is ever less than or equal to 0. And so you can do some algebra there, but if you also just think about function inputs and outputs, the outputs of an exponential function are not ever going to be negative. E to any power will not ever be negative. And so whatever I get from the outputs of that exponential function, I'm going to multiply by 3. That's still going to be positive, and then I'm going to add 1. Yeah, so that expression 1 plus 3e to the -2t is never 0 and never negative. So this is always positive. So that means that I don't run into any trouble with the radical and thinking about differentiability of this function. I do also have a negative exponent e to the -2t, which represents a denominator, 1 over e to the 2t, but e to the 2t again isn't ever 0, so you don't run into trouble with the denominator being 0 in that as well. So this function here is continuous and differentiable and satisfies the original differential equation on the interval -infinity to infinity.